All right, so today we're going to try to get to the bottom of fracture diagnostics.
Oh, cool.
Yeah, so basically we're going to try to figure out what's going on like miles underground when, people are doing hydraulic fracturing
Right.
and specifically how they track those fractures to make sure that, everything's going according to plan.
Okay.
And the main source we're going to be looking at for this deep dive is chapter 14 from this book, Hydraulic Fracturing.
Okay, so it's almost like imagine you've pumped all this, fluid and proppant downhole to create these fractures, but you can't see where they're going.
Right.
So how do you know? And that's where these diagnostics come in.
Okay, so it's like a treasure map, but instead of X marks the spot, it's like fracture marks the spot.
Yeah.
But how do you even start? I mean, how do you even track something that you can't see?
Well, the first thing you can look at is pressure changes because think about like blowing up a tire. Like the pressure gauge tells you how much air is going in and if there are any leaks.
Mm.
So similarly, you can track pressure downhole, and that'll give you an idea of how the fracture is accepting fluid, how it's growing, if there's any leakage.
That makes sense, but that sounds like you're just kind of guessing what's happening based on the pressure. Like, are there any ways to directly see, quote unquote, see the fractures?
Yeah, you're right. Pressure is more of an indirect measurement. It gives you clues, but doesn't really show you the fracture itself. But there are other techniques that get us much closer to, actually seeing what's happening.
Okay, so let's talk about what's going on closer to the wellbore.
Okay.
Because I imagine that, knowing what's happening right near, quote unquote, home
Mm-hmm.
is really important, especially if you want to make sure that, the right zones are being fractured.
Exactly. So we call those near wellbore diagnostics.
Okay.
And two of the techniques that are used are temperature surveys and radioactive tracers.
Wait, temperature. How can temperature tell you anything about a fracture?
Well, it might seem a little counterintuitive, but remember, the fracturing fluid that you're pumping downhole is usually at a much different temperature than the surrounding rocks.
Okay.
So as that fluid flows into the fracture, it creates this temperature difference that you can actually detect.
So it's like, if you pour like really hot water into like a cool glass,
Yeah.
you can kind of see the heat spreading out.
Yeah, exactly. Yeah. Like in the early days, they would run temperature surveys a couple hours apart, and they could actually see that cooling effect in, the targeted sand formation.
Wow, that's crazy.
Yeah.
So it's almost like a thermal fingerprint of the fracture.
Yeah, pretty much.
I imagine technology has come a long way since then, though.
Oh, absolutely. Yeah. So nowadays, you have these fiber optic cables that run along the wellbore, and those provide continuous real-time temperature readings.
Oh, wow.
So it's called a DTS, or a distributed temperature system. So instead of getting like, snapshots every couple hours, you're getting this constant stream of data.
Okay.
And get this, these DTS systems can actually also pick up acoustic data. So it's like listening to the wellbore.
Wait, hold on. So you're telling me that these temperature sensors can also act like microphones?
Well, yeah, kind of, yeah.
What will they think of next? Like, what kind of stuff can you actually hear, though, with these systems?
So there was this one case where a DTS system actually detected a packer leak.
Really?
Yeah, and it was pretty cool because the leak actually stopped itself when the proppant reached that point in the formation.
Oh, wow. So it's like the proppant acted like a plug, and the DTS system could actually hear all of that.
Yeah, exactly.
That's wild. So it really is like having like eyes and ears downhole.
Yeah.
Now, you also mentioned radioactive tracers. And that one sounds a bit, risky. Like, are we talking about injecting like radioactive materials underground?
Yes, but it's done in a way that's very safe and minimizes any kind of environmental impact.
Okay.
And the isotopes that they use actually decay very quickly. So, the technology has actually evolved a lot, and now they use it's called zero wash, where they actually incorporate the radioactive material into the proppant grains.
Okay.
So that significantly reduces any kind of risk of contamination because the tracer is only traveling where the proppant's going.
So it's like they're giving each little grain of proppant like a little tracking device.
Yeah, pretty much.
That's really cool. And then how do you actually detect these tracers? What do you use?
So they have these special tools called spectral gamma ray tools, or spectaskin.
Yeah.
And those can actually differentiate between different isotopes based on their unique gamma ray signatures.
So you can actually like pump in multiple types of tracers and still be able to tell which one's which. Cool. That's impressive. So you can see which zones took the most proppant and if the treatment was successful, right? So everything's radioactive these days, huh?
No, no, not at all.
Okay.
There's actually non-radioactive tracers as well, which use a compound called HTNCC,
Okay.
and that can be detected with neutron logs.
Okay, cool.
So there's, a lot of different options depending on what the specific needs of the project are and what the regulations are.
All right, that makes sense. So it sounds like, the temperature and the radioactive tracer logs give us a pretty good understanding of like what's going on right near the wellbore. But what about, for those fractures that extend further out?
Yeah, that's where far-field diagnostics come in,
Okay.
and we can talk about that more next time.
All right, cliffhanger. I can't wait.
Yeah.
But join us for part 2, where we'll actually explore how they map out the full reach of these fractures deep underground.
Sounds good. Welcome back. It's amazing how much we can learn about what's happening, like, thousands of feet underground.
It really is like having a superpower, being able to see through all that rock.
Yeah.
Last time we were talking about those near wellbore techniques like the DTS and the radioactive tracers.
Right.
Those are great for seeing what's happening, close to the wellbore. But
Yeah.
what about for those fractures that extend like way further out?
Yeah.
That's where the far field diagnostics come in, right?
Exactly. And one of the coolest techniques in this area is microseismic monitoring.
Okay.
So think of it this way. When a fracture grows, it actually creates these like tiny tremors in the rock,
Yeah.
almost like mini earthquakes.
Yeah.
Yeah, they're called microseismic events. And you can detect these with really sensitive sensors called geophones.
So we're basically listening to the rock as it cracks.
Yeah, pretty much.
That's so cool. I imagine you need a lot of those geophones, though, to be able to, like, actually pinpoint where the fracture is.
Yeah, it's all about triangulation. So we place arrays of these geophones, either downhole or on the surface, and by analyzing the arrival times of the different sound waves, we can actually figure out the exact location of each microseismic event.
Oh, wow.
So it's like using a GPS system, but for tracking fracture growth in real time.
So you can actually see the fracture extending outwards from the wellbore.
Yeah, exactly. It's like having this 3D map of the fracture as it develops. And this is really valuable, for understanding how the fracture is propagating through the reservoir and if it's reaching the zones that you're actually targeting.
Now, I have to ask, if we're talking about mini earthquakes, is there any concern about, like, triggering a larger, like, more damaging seismic event?
Well, that's a good question, and it's definitely something that scientists and engineers take very seriously, but it's important to remember that the microseismic events that we're talking about here are really tiny, like orders of magnitude weaker than earthquakes that people can actually feel. The International Gas Union, they actually published a report highlighting this difference, and they show that the seismic activity from hydraulic fracturing is usually like 100,000 times less than levels that are even detectable by humans.
Wow, that's okay.
Yeah.
So these are tremors that you wouldn't even notice unless you had, the special equipment to listen for them.
Right, exactly.
It's good to have that context because I think, like, the word earthquake just kind of automatically, like, makes people nervous.
Yeah, for sure.
All right, so we've talked about listening to the fractures.
Right.
What about some other far-field techniques? You mentioned tiltmeters earlier, and that one really stood out to me.
Yeah.
How can measuring, like, teeny tiny changes in the Earth's tilt, like, how can that tell you anything about fractures?
Well, it might sound hard to believe, but these instruments are super sensitive. Like, they can detect changes in ground slope on the order of arcseconds, which is, 1/3600th of a degree.
Wow, that's, like, mind-bogglingly small. How do those, like, tiny tilts relate to fractures, though?
So think about it this way. As a fracture grows, it kind of displaces the rock around it.
Okay.
So that causes these very subtle changes in the ground slope. And by placing, an array of these tilt meters around the wellbore, you can measure these changes and actually, like, visualize the shape and extent of the fracture.
So it's like watching the ground, like, subtly bulge and dip as the fracture grows?
Yeah, exactly.
That's crazy. But if these changes are so small, how can you be sure that it's the fracture that's causing them and not, like, other stuff like, traffic or even just, like, wind blowing on the sensors?
Yeah, that's a really good point. One of the challenges with tiltmeter measurements is filtering out all that background noise, to actually isolate the signal from the fracture.
Right.
There was actually this funny story about a project where, like, the circadian rhythm of a nearby turkey farm was interfering with the readings.
What?
Yeah, it was pretty wild.
The turkeys were messing up the data?
Yeah.
That's hilarious. Yeah, I guess that's why, like, careful planning and placement of these things is so important.
Oh, absolutely.
And obviously, having really sophisticated data processing to, like, remove all those extra signals.
Right.
Um, are there any limitations, though, to, like, what tilt meters can tell us?
Yeah, so for surface tiltmeter arrays, the depth is usually limited to around 8,000 feet. And for downhole tiltmeters, temperature becomes a constraint. They usually tap out around 280 degrees Fahrenheit.
Okay, so it seems like every technique kind of has its, like, strengths and weaknesses.
Right.
But I guess that's why it's so important to have, like, a whole toolbox of different methods, right?
Exactly. Because no single technique is going to give you the complete picture. But by combining data from multiple sources, you can start to, piece together a more comprehensive understanding of what's happening down there.
Okay, that makes sense. Speaking of piecing things together, let's talk about chemical tracers. Those seem like another important piece of the puzzle. Can you explain how they work and, like, what kind of information they give you?
Yeah, so chemical tracers are all about understanding fluid flow back.
Okay.
So remember, you inject all this fluid to create the fracture, but how much that fluid actually comes back to the surface?
Right.
And what path does it take?
Okay.
So chemical tracers help us answer those questions.
So it's like adding, like, a dye to the water and seeing where the color goes.
Yeah, that's a good way to think about it.
Okay.
We basically add specific molecules to the fracturing fluid at, known concentrations, and then we analyze the flowback samples to see where those tracers end up.
Oh.
So this can help us identify, which zones are contributing the most flowback, if there's any communication between different fracture stages, and how efficiently the treatment is performing overall.
So it's like tracing the footsteps of the fracturing fluid.
Yeah, pretty much.
I can see how this would be really helpful for optimizing production.
Exactly.
I remember reading a paper by a Saudi. He's like one of the leading researchers in this area.
Oh, yeah, I know him.
And he was using chemical tracers to actually distinguish between, like, fluid coming from different fracture stages.
That's right.
So it was like, a fingerprint for each stage.
Exactly, yeah. His work has been really important for advancing our understanding of these chemical tracer applications.
Oh, cool.
And he's actually, he's also compared the effectiveness of using, like, polymer concentrations versus chemical tracers for flowback analysis.
Oh, interesting.
Yeah, it's pretty fascinating stuff.
So it sounds like fracture diagnostics has really evolved a lot over the years, like from those early temperature and radioactive tracer logs to, these more sophisticated techniques like microseismic monitoring, tiltmeter arrays, and chemical tracers.
Yeah, absolutely. It's been an incredible journey of discovery.
It really has. And what I think is really cool is that each technique seems to like capture a different aspect of the fracture, like different facets of a gem.
I like that analogy. Yeah, it's
Yeah.
like we're putting together this complex 3D puzzle.
Exactly. But even with all these advanced tools, there's still some uncertainty in, like, interpreting the data.
Oh, absolutely.
Remember that quote we mentioned earlier about figuring out the truth, half-truths, and bold-faced lies?
Yeah.
It's a good reminder that even with the best technology, we're still dealing with incomplete data.
Mm.
And our interpretations are, always going to be subject to human limitations.
Right.
So it's a call for, like, humility in the face of complexity, recognizing that, we don't have all the answers.
I agree.
But that's part of what makes this field so exciting, right?
And absolutely.
It's this, like, constant pursuit of knowledge and understanding.
Yeah.
So what's next in our exploration of fracture diagnostics?
Well, let's take a look at the future of this field and what exciting innovations might be on the horizon.
Okay, sounds good. So, as we're wrapping up our deep dive into fracture diagnostics, it's pretty amazing to see how far we've come in understanding what's going on, like, miles below the surface.
Oh, it really is.
It's like we've been on this journey to the center of the earth,
Yeah.
using all these cool tools to map out this, like, invisible world of fractures.
It really is a testament to human ingenuity. We've gone from basic temperature surveys to these super sophisticated techniques like microseismic and tiltmeters, all to understand these, like, tiny cracks in the rock that could unlock huge energy resources.
Yeah. And, in the last part, you were talking about some really, like, mind-blowing possibilities for the future of fracture diagnostics.
Right.
Specifically, like, integrating all these different techniques.
Yes.
And also harnessing the power of AI.
Yeah.
Can you tell us a little bit more about that?
Okay, so imagine this. You're an engineer, and you have this real-time 4D model of the fracture as it's happening. You're seeing the microseismic data, the tiltmeter measurements, the chemical tracer analysis, all combine into one big dynamic picture.
Okay.
So you can see how different zones are responding to the treatment, identify potential problems like proppant screen out,
Right.
and even adjust the treatment parameters on the fly.
You would be like having X-ray vision for like the subsurface.
Yeah, exactly.
You can see exactly where those fractures are going, how they're growing, how the fluid's flowing through them. That's like a dream come true for, anyone trying to optimize these treatments.
Exactly. And with AI and machine learning, we can take it even a step further.
Sure.
Imagine a system that can analyze huge amounts of data from previous treatments, learn from past successes and failures,
Oh, wow.
and make real-time recommendations to optimize the current fracture job. It would be like having a super intelligent assistant guiding every step of the process.
That's incredible. It's like having a GPS for your hydraulic fracturing treatment,
Right.
guiding you to the best outcome. But it also makes me think about, the bigger picture. Like, what do all these advancements mean for, the future of energy production
Right.
and like a relationship with the subsurface?
That's a really great question. I think as our ability to understand and manipulate the subsurface grows, we really need to be mindful of the ethical and environmental implications. We have a responsibility to use these technologies wisely, minimizing risks and making sure that they benefit both people and the planet.
Absolutely. It's like a reminder that technological progress should always be guided by, a sense of responsibility
Yes.
and sustainability. We have a powerful set of tools,
Yeah.
and it's up to us to use them in a way that creates a brighter future for everyone.
Very well said. And as we wrap up this deep dive into the world of fracture diagnostics, I hope it's left you with a sense of wonder and excitement for what the future holds. This is a field that's constantly pushing the boundaries of knowledge, and who knows what incredible discoveries await us in the years to come.
This has been an awesome, eye-opening experience, and I want to thank you for, sharing your expertise and your insights with us.
My pleasure.
And to our listeners, thank you for joining us on this incredible journey to the depths of the Earth. We hope you've enjoyed the ride, and we hope that you'll continue to, explore and question and dive deep into this fascinating world around us. Until next time, keep those brains buzzing and those curiosities ignited.